Okay, good morning. Well, looking at the classroom, I can say it's Friday, even if I didn't know it. Couple of announcements first. I will hold class as usual next week. While I agree with why CFA is striking, and obviously it's to my benefit if my salaries increase, which actually doesn't keep up with the cost of living anyway. The people who end up suffering are the students. Then there's the issue of the labs. We only have like 8 labs, and I teach one of my labs on a Tuesday. So if I didn't hold lab next week, the actual first lab the class would have would be in week 4, which is kind of insane when I think about it. Anyway, the point is that I plan to be here. I will be in person in this classroom, teaching the same as usual, in person as well as online. Students always have the option of attending class in person or online. You don't have to let me know. That's the first point. Second point is quiz as usual on Mondays. So we will have a quiz beginning of class. My classes begin at 9 o'clock, and I usually come on campus via bus at 8:15. So I don't know what the situation is going to be on Monday, but your class does not begin until 11. So, even if I'm late, I would be late for the 9 a.m. class, not for yours. Yours should be beginning on time. That's as far as the class goes. The quiz, I usually post an announcement on Canvas, so it's usually all there in one place. I think for quiz 1, I sent an email. I did not post an announcement. But again, what I do is I post an announcement noting the quiz, the date, the topic under assessment, as well as the prep material, what the students need to do to prep for the quiz. And it is always based on the material that I covered in class in the preceding week. Meaning if there's a quiz on Monday, it covers the topics from the previous Monday, Wednesday, Friday. So the material that we learned this week, Monday, Wednesday, Friday, will be the topic that is going to be assessed next week. Homework also right now, so that's the third point actually. Homework assignments are all set for June. Again, they were just a placeholder dates because the system will not allow me to make it available to all students without there being a due date on it. So I just put a due date like at the end of the academic calendar. This is like the end of spring quarter. But again, if you look at my syllabus, and I also mentioned this on the first day of class, homework is automatically considered assigned once the topic is covered in class. So if I cover KVL in class, KVL is automatically assigned. If I cover KCL in class, it's automatically assigned. We're covering series parallel equivalent analysis technique, that would be automatically assigned. The due dates might shift depending on how fast or slow we go in class, but it'd just be like a day or two. And that is the purpose of integration. So my Pearson homeworks are integrated inside Canvas. And one of the reasons I do that integration is so that the assignment due dates show up on your Canvas calendars. So again, it is the responsibility of the students to be on time by looking at their calendars. Okay. All right. So having said that, are there any questions? Okay. So then let's move on to our topic of discussion, topic under discussion. And that would be, let's see, where did we go? New share. And this is for section 4. So we did, okay, we solved this problem. Now we are here. Calculate currents. The 3 examples for okay. All right, so the 3 examples for the series parallel analysis technique. Series parallel analysis technique is a larger method. And inside this technique, you can apply Ohm's law, KCL, KVL. Oh, that is one more point. So I just mentioned that the topic under assessment for a quiz would always be the topic that we covered in the preceding week. Okay, I will not specifically ask you anything from the prior weeks. But having said that, it does not mean that students would not need that knowledge. So for next week, I will assess on series parallel analysis technique, but you still need to have knowledge of Ohm's law, KVL, KCL, power, energy, etc. Does that make sense? I will not specifically test you on KVL. I'm not going to specifically test you on Ohm's law, but you do need to know those, to solve for that week's problem. Does that make sense to students? Okay. All right. So in this case, we have 3 circuits. We're going to look at all 3 of them. We start with A. And the first step is to remove the source. From the rest of the circuit. So I have open terminals. And once I have open terminals, I can find Req. So I have R1, R2, R3, R4. I have Vs here. And I have to find Req between terminals A and B. Between A and B. Okay. Source Vs is supplying a current. Which direction is that current going? Up or down? Up, because the source is supplying, we put a minus sign on it, and it goes from minus to plus. The current coming out from that voltage source, Vs, has nowhere else to go except through R1. So what can we say about the relationship between I and I1? They're exactly the same, right? It's the exact same current. Then once I or I1 hits this junction, it splits into 3 parts, going down R2, R3, and R4. So then I get I2, I3, and I4. And to make our jobs easier, of course, the directions are always given. Okay. One point to note, a voltage source, if it didn't have current going from minus to plus, it would not make logical sense, right? We would not have a minus sign in front of that. It's supplying. So mathematically, we say it's minus or going in the opposite direction. But electrically speaking, is simply supplying. Okay, coming back to our circuit, Req, starting at the farthest end, I have R4. And I can see R4 is in parallel with R3, is in parallel with R2. Right? So R4 in parallel with R3, in parallel with R2. I can say I can assume and note this as R5. So that's the parallel combination of R2, R3, and R4. Okay? R2, R3, and R4. You guys with me so far? Okay. Then I had current I1 going through R1, right? That current has nowhere else to go except through R5. So the exact same current also goes through R5. R5 is a combination of 3 resistors, but right now we're treating them as one. Same current flows through R1 and R5. And that one is in series with R1. So my total Req is 40 in parallel with 20 plus 10. Someone do this calculation for me, please. Up to 4 decimal places. 4. 08. Yeah. So it would be 19.2308 ohms. There is a reason I'm going to 4 decimal places. It's because if I take 2, my answer is going to be a little bit different, which is again fine. So in the exam, if some students take 2 places or 3 or 4, the answers are going to be a little bit different. But I will give full credit. If the method and the steps are correct, I will give full credit. So REQ is 19.2308. Therefore, my I, again, 20 divided by 19.2308. What is this number? 2.2. It's 19. 19. 9 was for R6. Sorry, R5. So what do you say? 1.04. 1.04. So 1.04 amps is going through R1 and R5. I've reduced my circuit. Now is the time to expand it back up again in the reverse order. I can find the voltage across R1 and R5 by simply applying Ohm's law again. And so, sorry. VR1 is simply I times R1. So 1.04 times what, 10? Gives me 10.4 amps, 10.4 volts. And VR5, I can find using Ohm's law, or I can apply KVL. 1.04 times what, 9.2308. What do I get? 1.04 into 9.2308. 9.6 volts. If I applied KVL, I would have VR phi is equal to Vs minus VR1, which would still be 9.6 volts. Take 10-second pause, think over it, and let me know if you have any questions. $20 volts being applied to R1 and R5. It's 1 voltage. I'm sorry, 3 voltages in that loop. You have the value of 2 of them. The third one is straightforward. So you can apply KVL to find it, or you can apply Ohm's law to find it. Multiple analysis techniques that you can apply within the larger method. Okay, you can choose which one you wish to use. If I didn't take 4 decimal places in REQ, which is right here, 9.2308 for finding R5, it would be either 9.23 or it would be 9.23. If it was 9.23, my current would be 1.05, I believe. It's 1.05. This would change and this would change. Would not get exactly 9.6. It's a little bit different answer. Anyway, does the analysis method make sense? Right? You reduce a large network of resistors down to one single resistance, apply Ohm's law, you find the voltage or you find the current, depending on what the source is, and then you expand the circuit back up again in the exact reverse order. And at every step of expansion, you apply Ohm's law or KCL or KVL to find the voltages and the currents in the other parts of the circuit. Yes. So the question being asked is, when we expand the circuit, do I want to see the image? The answer is no. As long as the equations that you write out make sense, well, sorry, let me back up a little bit. What students need to understand is that you are showing your understanding of the topic, so I can assess that knowledge. I can assess that understanding. If the work is not shown, I have no basis for judgment, so I cannot award any points. So you can either show it using images and circuit diagrams, or you can show it by writing the equations out and then solving them, right? Your choice. You can show it using circuit diagrams or the circuit schematics when you expand it again, or you can write out the equations as I've done on the board. Either way is your choice. But your work must be shown. If the work is not shown, if it's blank, I cannot judge a blank piece of paper. I cannot judge a blank space, right? If I ask you to solve something using Ohm's law and you just write out, oh, V is equal to 20 volts. Okay, you have the answer, but how do I assess whether you know how to apply Ohm's law or not? Does that make sense to students? So show your work always. And that is good advice for your entire academic career as well as professional career. Always show the work that you're doing, right? If you go work out in the industry, you always want to show that you're doing the work. The end results matter, of course. As long as the results are accomplished, they don't need to see what and how you did it. But again, it's just a good advice to follow. Okay, and once you have voltages across all components, you can find the currents flowing through every part of the circuit. So in this case, when we expand the circuit, my VR phi this is VR1, and this is VR5. And VR5 is the same for all three resistors, right? It's a parallel combination. Important thing to keep in mind, again, it's kind of repetitive, but the voltage that appears across a parallel network of resistors is a result of all those resistors acting together or working together. Okay. So when you say VR5 is the same for R2, R3, and R4, well, it's the result of R2, R3, and R4 all working together. And that's why it's the same. Parallel network, 2 points. If you take any one of those resistors out, now the Req has changed. So the voltage value will change, but whatever that value is, it will still remain the same for the parallel resistors. Okay. So VR5 we found as, what did we find it as? 9.6 volts. So 9.6 volts appears across R2, R3, and R4. Okay. If I take R4 out of that circuit, now my 9.6 would change to something else. But it will still be the same for R2 and R3 because they are in parallel. That's the important thing to keep in mind. It will not stay as 9.6. All right, any questions? Once you find the voltage, simply apply Ohm's law, find I2, I3, and I4. Okay. Make sense? All right, let's take a look at B. We'll solve this using intuition and logic first. What do you see? We have a current source IS, 2 amps, going down this pathway. It splits in two. It splits into I1 and I2. What do you notice about these two resistors? Series or parallel? Series, how about this? Values? So 20. So my current is splitting in two. branches, but the opposition is exactly the same in both branches, what do I expect to see? Same values in both, exactly. I1 and I2 have the exact same values. Two parts, meaning divided in equal halves. Two parts, but both parts are equal. So if I solve it using logic and intuition, what do I see I1 and I2 as? 1 plus 1, right? So let's solve this using our, well, harder analysis techniques. If we reduce this circuit, let's first remove the source. The source is on the side. And I have R1, R2, R3, R4. When current flows through a resistor, I would assume a voltage would appear. That voltage would remain the same because the terminals are the same. Okay, it's the same parallel node, the same junction. So anything connected between that junction will have the exact same voltage. I'll call that voltage as V. Let's first find Req. Req would be equal to the series combination of R1 and R2 in parallel with the series combination of R3 and R4, right? These two branches are parallel. So it would simply be 20 parallel 20. What do I get? Two ways to solve it. Product of the two divided by the sum of the two, or X over N. Parallel resistances, same branches in parallel, divided by the number of resistors in that network. So 20 divided by 2. Or 400 divided by 40. I'll pause. Or you can do it the old-fashioned way by using your calculators. Yes. Well, that's what I did at first, right? Just solved it using logic and intuition. But no, if I'm asking you to solve a circuit, it's not going to be this easy. Maybe some weird number. 5.78.1x minus 3 something something. No, not that complicated. But anyway, the examples are chosen such that it's easier for students to understand at the beginning. That reminds me of a joke about elementary school kids where teacher solves like a simple math problem on the board and asks the students to solve, okay, now you show me how to do this. So teacher shows 2 plus 2 and then asks the students to solve like 5 plus 8. The student says it's not fair. And the teacher says, why is it not fair? Says, you get to solve the easy ones and we get the hard ones. And so it's kind of like, it reminds me of that joke. Okay, I like these examples because they are nice round numbers. They give, except for this problem where you had like a 0.2308. Most of the examples that I've chosen here, they're rather straightforward and you get it easy. But the point again of these examples is to show or illustrate to students the method, right? So if I'm teaching you a method, I'm going to assess students on that particular method, and then I expect to see that method on paper, on the solution. So 10 ohms. So now my Req is 10. My V in this case is I times Req. And so it's 2 times 10, 20 volts. 20 volts is applied to both branches. And so I can write I1 is V divided by R1 plus R2. 20 over 20 gives me 1 amp. I2 is also the same, V divided by R3 plus R4, also 20 divided by 20, 1 amp, which is what we obtained at the beginning, right? We just split it in half and we get two halves and we get 1 and 1. But leaving logic aside, does the procedure make sense? The method, that's the more important point. All right, 10-second pause. Let me know if you have any questions. Any questions at all? Okay, let's look at C. We have a voltage source 30 and 4 resistors in the circuit. I'm just going to redraw that circuit. And once I redraw the circuit, I have a voltage source here, R1, R2, R3, and R4. Oh, I should have removed this. So remove it from the source. Remove it from the circuit. Terminals open, A and B. Those terminals are my measurement terminals. So REQ between those terminals, I start at the farthest end. I get R4 plus R3 in series. They're connected only at one terminal each. So between the outer terminals, R3 and R4 are in series, which would be in parallel with R2, which would again be in series with R1. I'm going to call R3 and R4 as 5, and R5 parallel R2 as R6. Does everyone see that? Yes. No, because the terminals R4 is not connected directly to R2, right? For it to be in parallel, the terminal has to be connected. It's connected here, but it's not connected here directly. It's connected via R3. So we could also draw the circuit as like this. I would have R1 here. I have R2 here, R3 here, and R4 here. Does that make sense? Okay. All right, so R3 and R4 are in series, and that series combination is in parallel with R2. And then once we reduce R2, R3, and R4 to one single resistance, we can see that it'll be in series with R1. And again, at the beginning of this quarter, I mentioned that I'll take it slow at the beginning, but then students need to get adept and an expert at applying these techniques in applying series parallel techniques quickly and efficiently and correctly. Yes, you had a question. So for it to be in series, there cannot be more than 2 connections at the junction. Yeah, so the junction here, so the question being asked is why is R2 and R1 not in series at the beginning? And the reason is at this node, you have R3 connected. So if it was more than 2 connections, you cannot have a series connection. But later on, when we reduce it to one single resistance, so if it's R1, and then R2, R3, and R4 are now reduced to R6. Again, R6 is not the same as R2. Okay. Now we can say it's in series because it's only one single terminal. There's nothing else connected. Okay. R6 is not the same as R2. All right. Yes. Nope. Yes. R3, 4, R Batman, Iron Man, anything. Batman is just longer to write, so. But you can call it anything you want. Students can name it anything. I just use single, I'm lazy that way. R3, 4 takes more effort than writing just R5. Anyway, enough jokes. Let's see, where was I? Oh, REQ. So REQ in this case, again, nice round numbers, and you will see R3 and R4. Let's go back to the values up top. What do we see? 40, and then 40 is in parallel with 40. So REQ is 40 in parallel with 40 plus what is R1? 10. This is 20 plus 10 gives me 30 ohms. My supply voltage Vs is also 30. I have one single resistance. So now is the time to apply Ohm's law. From Ohm's law, I can write total current I is equal to Vs or REQ, which gives me 30 volts divided by 30, 1 amp. Right? 30 volts divided by REQ, which is 30, gives me 1 amp. And at the beginning of analysis, we see that I1 is equal to I, similar to problem number A or example number A. I going around the circuit would be the same as I1, similar to example A at this point. In A, what do we have in A? These two are the same so far. R3 and R4 are in parallel in this case, and they are in series in this case. That's the only difference. Do you all see that? Right? R1, R2, and the source are exactly the same. It's R3 and R4 are in parallel in one case, and they are in series in the other one. That's it. That's the only difference. So all other concepts remain the same. And again, for every topic, I could have like 10 different examples, different circuits, different concepts, everything. I could sit here all day long and just do it. But in the interest of time constraints, we cannot do every single example. So this is 1 amp. Then at this point, I can say my 1 amp is being split in two. Right? The same 1 amp is going through R1 as well as R6. R6 is a combination of R2. So I1, and then it splits in two. But both branches are exactly the same. So I know what my answer is going to be, right? As you just asked a little while ago, can we just state it's the same? Well, the answer is no, you cannot simply state it's the same. You have to show the work. And so in this case, I can write VR6 is equal to R6 times I. R6 is 20 times I, 20 volts. VR1 is I times R1. That's 10 times 1, or 1 times 10, 20 volts. You can find one voltage and find the other one by applying KVL, or you can apply Ohm's law for both. Doesn't really matter. 30 volt supply. If you subtract 10, you get 20. 30 volt supply, if you subtract 20, you get 10. Or you apply Ohm's law to both. 10 times 1 is 10, and 20 times 1 is 20. 10 plus 20 is 30. Multiple ways to solve the same problem. Once you have voltage across all of those, you can simply apply Ohm's law again, find the current. So 20 volts divided by 20 R2 gives you, sorry, not 20, 40. So I2 is VR6 divided by R6. Sorry, not R6. What am I doing? VR6 divided by R2. 20 divided by 40 is 0.5 amps. At this point, I can apply KCL. 1 amp minus 0.5 gives me 0.5 amps. Or I can apply Ohm's law again. And I3 can be VR6 divided by R5. Again, 20 divided by 40. Or you apply KCL. Gives me I3 is equal to I minus I2, 0.5 amps. Either ways. Once you have voltage, once you have current, you can find power, energy, as the case may be. Is the method clear to everyone? Any questions? Okay. So at this point, I'd like to go back a few slides and show you a technique that I came up with, and we'll use example B to solve this technique or to solve REQ. So example B, what did I have? I have R1, R2, R3, and R4. And I'm asked to find the total equivalent resistance between A and B. So in this technique, what you're going to do is you're going to first start out by drawing two horizontal lines. So spaced far apart. Okay. These horizontal lines are signifying the measurement terminals A and B. Now, when we try to reduce a circuit to one single resistance, it is not always possible. Some circuits are non-reducible. So mathematically or graphically speaking, okay, you can, if it's a real circuit, in real life physical circuit, you can take a measurement meter and you can put it across terminals and you can measure it right away. Very easy to do so. But all circuits are not reducible. But for circuits that are reducible, this technique will work on all of them. So first step, as I was saying, you take your measurement terminals and you draw out two horizontal lines noting those terminals. You want them spaced far apart so that you have enough area to actually draw out your circuit. The goal in this technique is to go from A to B for every single resistor that is connected. And you draw them vertically. Okay, you draw them vertically going from A to B. Okay, so let's start with terminal number A. What do we have connected at A? What resistors are connected at A? R1 and R2. Okay, so we drop them vertically. Again, leave enough space so that you can draw out your circuit. So R1 and R2 dropped vertically. Anything else connected at A? No. So we'll move on. Let's go to the other end of R1 so we can complete that branch. Where is R1 going? The other end of R1 is directly going to terminal B. We don't have to do anything. Simply drop the other terminal of A sorry, R1 all the way to B. We're done with that branch. So far, so good. Then we take the other end of R2. What is connected at the other end of R2? R3 and R4. So I'm going to do kind of like a flow chart. R3 and R4. Goal is to get to terminal number B. So we can either choose R3 or R4. Doesn't really matter in this case. If you choose R4, where is R4 going? R4 is going directly to B. So we drop a line going directly to B. Then we come back to R3. Where is R3 going? R3 is also going directly to B. So we simply drop a line going to B. And that's it. Once we have all the resistors accounted for, we have now assigned different branches, right? So R1 is one branch, R2, 3, 4 is another branch. If you had more resistors, you'd have another branch, and so on and so forth. The beauty of this technique is that every single branch that you write out will all be in parallel. Every single branch will be in parallel. So all you have to do is reduce all the resistors in single branches, all of them down to one single resistor. And at the end, all you have is a bunch of resistors in parallel. Make sense? So in this case, R1 is single by itself, so we don't have to worry about it. We get to R2, R3, and R4. R2 is neither in series nor in parallel with R3 and R4 right now. So the first step is to reduce R3 and R4. R3 and R4 are in parallel. We can see that because they're connected at the top and at the bottom. So R3 and R4 are in parallel. And then they would be in series with R2. And then finally, of course, that entire branch is in parallel with R1. It's exactly the same as we found here. Make sense? This technique will work on all circuits, all reducible circuits. There is a homework problem where the circuit is diamond shaped, just drawn differently with a short coming from the top to the bottom. You apply this technique to that circuit and you'll be done in minutes. Yes. Yes. We will look at that in like next week. So we'll learn about different analysis. The reason we have different analysis techniques is because all circuits cannot be solved with one single technique. And so that's the point of using different techniques. Okay. Let's see. Any questions about this technique? As I said, there was 2 homework problems in separate homework where you have that diamond shape technique, and you can solve them using this. Let's see. I want to. We have time, and we need to get to voltage division. So let me at least introduce the concept. Voltage division. Voltage division principle states that if you apply a voltage to a series connection of resistors, a fraction of that voltage appears across each resistor. And the fraction is given by the ratio of the resistor to the total equivalent resistance in that network. It's quite a mouthful, but I will explain the derivation. It's not that difficult. It's just that the word explanation is kind of lengthy. So voltage total being applied, I have current I going in this direction, it goes through here. And there is nowhere else for it to go in a series connection. So the current is exactly the same. Does that make sense? There's no other pathway for the current to go through. So if it's a series connection, the current is the same for the entire circuit. From Ohm's law, I can write my total current I is equal to V total divided by Req. Req in this case is simply the sum of all the resistors in that series connection. R1 plus R2 plus R3. Now again, we apply Ohm's law in the reverse. And again, VR1 is equal to I times R1. Plug in and rearrange the values. R1 or Req, or R1 over R1 plus R2 plus R3. That's it. That's the voltage division principle. Wait until students finish writing. Okay, so coming back to that word definition. What I stated was when you apply a voltage, V total, to a series network of resistors, a fraction of that voltage appears across each resistor. So VT being applied to R1, R2, R3, and R4, a fraction appears across each resistor, and that fraction is determined by the ratio of that resistor to the sum of all the resistors. So VR1 is a fraction of VT, and that fraction is given by the ratio of R1 to Req. That's it. That's voltage division principle. R1 over R1 plus R2 plus R3. VR2 in the same case be VT times R2 over Req. VR3 be VT times R3 over Req. Does that make sense to everyone? So if I was to solve this, what is my Req? 10. 10K. 10 kilo ohms. The electrical engineers like to take shortcuts, so we simply say like 10K or 5.7K. We ignore the ohms. But it's 10 kilo ohms or 10K. So Req is 10K. VR1 would simply be 15 volts times R1, which is 1, divided by 10. So I get 1.5 volts. R2 and R1 are the same. So I can write VR2 is also equal to VR1, 1.5 volts. Logic and intuition, R3 is twice as much as R2. So even without solving, I know it should be 3 volts. VR3 is 15 volts times 2000 divided by 10,000 gives me 3 volts. And of course, VR4 is 15 into 6,000 divided by 10,000. Comes out to be 9 volts. Apply KVL as a check. 9 plus 3 plus 1.5 plus 1.5 sums up to 15 volts. Yes. 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 So the question being asked is whether this works if it's part of a larger circuit, and the answer is yes. That is actually the point of this principle. If we take it one step back in this slide, oh, sorry, not this slide. Actually, I skipped over this slide. This is where the derivation was supposed to be. Anyway, if you notice, we found VR6 between these terminals, right? So the question being asked was, how do we apply this to a larger circuit? And the answer is like right here. So we found VR6 right here. VR6 is applied through R3 and R4. You can calculate the voltage across R3 and R4 by voltage division. See, R3 plus R4 is what? 40, right? So if you apply voltage division principle to calculate VR6, so VR3 would be given by VR6 times R3 divided by R3 plus R4. That would be the equation. So on that note, I think I've gone over a minute and a half over time. We'll stop right here. You'll look at this equation and see whether you get the right answer or not. Again, have a good weekend, and I will see you all on Monday.